So I have the enviable task of trying to explain some of the more technical concepts behind cryptocurrencies that you might have heard about. Consensus algorithms, sharding, scalability, performance. But we're going to do this together, okay? We're going to get through this. And by the end of it, I hope that you feel like you have a better understanding about how some of these systems work. So to introduce myself a little bit, I am the director of the Digital Currency Initiative, which is based out of the MIT Media Lab. I'm here to talk to you today about consensus. Why are we even talking about this problem? Well, the public's faith in institutions is at an all-time low. So what I'm showing you here is the bottom portion of a Gallup poll that is tracking confidence in institutions. These are the institutions in which the public has the least amount of confidence. So banks are definitely bad, with only 32% confidence, but they're not the worst. There are problems in media, big business, law. All of these institutions are structured in a hierarchical, top-down way. People don't really have enough visibility into how they work, and so they don't trust them. And to be clear, this problem is getting worse with future generations. Institutions have a lot of influence over our lives, but I think it's worth asking the question, how might we empower people to organize without institutions? How can we empower people so that they have more visibility into how institutions actually work? Well, in 2008, a shadowy figure known only by the name of Satoshi Nakamoto answered this question, at least for the field of financial payments. The answer was a new form of digital value transfer called Bitcoin. Satoshi released a white paper on the internet in late 2008, and I think that the most important sentence of the paper is right there at the very, very beginning in the abstract. This was a system that would allow online payments to be sent directly from one party to another without going through a financial institution. It took me a little while to realize this, but this was actually the first time that this had ever happened. This was the first time we could make online digital payments without a bank or another financial institution in the middle. Now, as we're going to see, and we talk about this, this is a little bit of a conundrum to get your head around, because despite the fact that it's not necessarily going through a financial institution, it's kind of going through everybody. So early the next year, Satoshi released running code, and people started running what is now known as the Bitcoin blockchain. They started becoming part of the network. This is a block. This is actually the first block in the Bitcoin blockchain. It's called the Genesis block. And don't try to read it. This is not really human readable. It's encoded for computers. But there is a little part of it that you might be able to read. And this is a line that Satoshi chose to embed in this Genesis block. It says, "The Times, January 2009, Chancellor on brink of second bailout for banks." So this line corresponded to a headline from January 4th, 2009. Satoshi included it to prove that he, she, or they, we don't know, started creating this blockchain on that date, that they couldn't have started before then because they wouldn't have known what the headline was. But more than that, I think including this headline spoke to what was at the time this growing distrust around these institutions that were deemed too big to fail, and the growing consolidation of power in our financial system. So this is some of the reasoning why we're even here today, why we're exploring this process. Because what came out of Bitcoin is a new way of thinking about how to build systems. So what I'm here to talk to you today is this concept of consensus, which underlies how Bitcoin works. We'll discuss how this is used in blockchains, and we'll talk a little bit about decentralization, what it means, and some of the remaining challenges. So let's start with consensus. What is consensus? Well, consensus, very simply, is the problem in computer science of how to get a bunch of computers distributed around the internet to agree on a value in the presence of faults. Our overlying goal here is that we want to make this system of computers, which might have different inputs, look like one single global computer. And even if some of those computers fail, as long as it's not too many, we can still reliably reach agreement. Consensus is actually a pretty old problem. It was formulated in the late 70s, 80s. And surprisingly, we can actually do better than just failure. There's a set of systems called Byzantine fault-tolerant systems. Now, what does this mean? You might have heard of the Byzantine generals problem. The Byzantine generals problem, first formulated by Leslie Lamport, winner of the Turing Award, and his co-authors, is described as such. You have a set of generals who are surrounding a city. Now, they can only take the city if they all attack at once. If they don't all attack at once, they might fail and suffer heavy losses. So these generals, which are encamped around the city, are trying to communicate to decide if they're going to attack or not. But there are traitors who are actively trying to subvert the generals and trying to screw them up so that only a few may attack while the rest stay back. This is the idea behind Byzantine consensus, that we can tolerate not just computers failing, but we can actually tolerate malicious adversaries on the network who might be trying to subvert agreement. It's pretty cool that we can actually do this. So, like I said, consensus is a pretty old problem. Leslie Lamport formulated the Byzantine generals problem in the early 80s. A form of consensus, an algorithm specifically called Paxos and variants, are used inside most large companies today in order to control sort of the scheduling and the design of their data centers. So consensus sits inside most of the internet services that we use today. In 1999, 10 years before Bitcoin, an algorithm called practical Byzantine fault-tolerant consensus was formulated at MIT by Barbara Liskov and her student Miguel Castro. And interestingly enough, though industry didn't really take this algorithm and do anything with it, now it's finding new life in permissioned blockchains. So permissioned blockchains are actually reaching back to 1999 to use this algorithm. In 2009, Bitcoin was introduced, and since then, we've seen a flourishing in absolutely new types of consensus algorithms. We've seen proof of stake develop, and we've also seen something called delegated proof of stake, and I'll talk about these a little bit further on. So let's discuss how consensus is actually used inside of blockchains. Well, there's two classes of blockchains, which you might have heard about, permissioned and permissionless. So just to go over this, the idea behind permissioned blockchains is you know everyone you're trying to reach agreement with. It's identity-based voting. You have a set of peers, you know who they are, and you're trying to reach agreement. This is very much like the classical consensus protocols on the left side of that timeline. What we saw with Bitcoin was a new type of environment. In this environment, you didn't know a priori who you were interacting with. You didn't know who you were necessarily going to be reaching agreement with. And so these systems are called permissionless. And the really key idea here, the really cool idea behind Bitcoin and its successors, was that these systems guaranteed security based on incentives. So let's talk a little bit about why this was such a hard problem that we didn't really get around to it until 2009. Well, you see, in traditional consensus systems, participation is based on identity, because most of them are voting protocols. Everyone in the system sends around messages, and they all vote, for example, for what they think the next block in the blockchain should be. If you try to apply this directly to a permissionless system, you're going to have a problem, because the attacker, since it's permissionless, can just make up identities and make up votes. This is what's known as a Sybil attack. With blockchains, since we're operating in this trustless, permissionless environment, we need something else. That was the insight behind Bitcoin. We were going to address the Sybil attack problem by making these identities actually cost something. So they weren't set ahead of time, but they were allocated according to how much people were willing to participate or pay. So let's talk a little bit about the different types of incentive-based consensus algorithms. I think that there are three major categories: proof of work, proof of stake, and delegated proof of stake. So let's start with proof of work. This is a data center full of what are known as ASIC miners. This is an industry called mining. It's producing Bitcoin and securing the blockchain network from electricity. Because you see, what happened was Satoshi had this really great democratic design for how Bitcoin should work. The mining process is one where you try a lot of random numbers in order to find one that solves a puzzle. And Satoshi envisioned that people would run this on their computers, on their laptops. Now, what happened was Bitcoin became so valuable that people were actually incentivized to create specialized hardware to do this random number checking very, very, very fast, millions of times faster than what I could do on my laptop. And it spawned this entire industry. So proof of work has been, though it consumes a lot of electricity, it requires a lot of electricity to run this specialized hardware, has been working pretty reliably for 10 years. It's very impressive, actually. A lot of people never thought that it would work. But Bitcoin has been chugging along and has not really been compromised on the protocol level. Now, people don't really like this electricity usage with good reason. And so people developed what are called proof-of-stake protocols. Now, the idea here is that we're also using incentives. It's also kind of permissionless, but the idea is that we'll assign votes based on how much money you have in the system. So people have different amounts of money, they have different ideas for what the next block should be, and you'll reach agreement based on your proportion of stake. That's why it's called proof of stake. So this is obviously a lot greener, doesn't require the same energy usage since you're not churning through many random numbers, but there are a few concerns to be had. This sounds very much like the rich get richer sort of a scenario. The more stake you have, the more likely you are to find the next block, the more likely you are to get a reward. It's also a bit less tested. We've only really seen robust proof-of-stake systems released into the wild in the last couple of years. So I think there's still a lot to be learned about proof-of-stake. Now, another technique, kind of related to proof-of-stake, is delegated proof-of-stake. And the idea here is that you'll use your stake to vote for validators. You'll elect these validators. And you know, maybe it's 101, maybe it's 27, maybe it's 21, but there's a set number of validators who are going to use something more like those classic consensus protocols to reach agreement. So look at these numbers up here. These are not very large numbers. In proof-of-work protocols, there are thousands of participants who are working on creating the blockchain. Here, you have 21. There are trade-offs when you do something like this. Because there's a smaller number of people engaging in the protocol, you can get higher transaction throughput. You can get better performance. However, there's also a smaller number of people participating in the protocol, meaning it might be easier to coerce them. So no matter what consensus protocol you're using, it almost always looks something like this when it's actually used in the blockchain. You're going to have a set of network nodes, computers, hopefully located around the world, that are running this protocol. They're using it to agree on blocks that form an append-only ledger, or blockchain. And what goes in those blocks can vary. In Bitcoin, it's transactions. In other blockchains, it might be records or something more complicated. And then every single node can construct an auditable, verifiable database view on top of this append-only ledger. This is really the key insight here. And the reason that it's auditable and verifiable is because we're using cryptography, hash functions, and digital signatures in order to enable people to verify all of the things that have been added to the blockchain. And because everyone's working off the same blockchain, when they run it in order, they all get the same view. Now, a big question here is, who gets to join that network? Do you have to ask for permission? Is it only a small number of people? Do you have to buy the cryptocurrency? This gets us into the question of decentralization. Now, decentralization is a word that's being thrown around a lot right now, surprisingly to me, by regulators, because I don't think we actually know how to define decentralization very well yet. It's a pretty complex topic, and I think simple mechanisms for trying to define it and trying to use it as a measure could pretty easily be gamed. So let's talk about decentralization a little bit. I'm going to define a decentralized system as one in which there is no single organization in control and there's no single point of failure. And I'm going to amend that to also include a small number of organizations in control. So what does this mean? Let's take Instagram, for example. Instagram is run by a company, Facebook. Now, if Facebook disappears, so does Instagram. My photos, my comments, my friends, my messages, everything gone. Facebook is Instagram. Facebook runs the servers. Facebook provides the application. I can't run it without them. In a decentralized system, it's quite different. The idea here is even an entire company could go away, and because of the protocol, because there's so many different participants, we can still run the application. It can still proceed. So let's talk about control. What does it really mean? Because you see, I think decentralization is actually a proxy for other features that we might want to have. Things like fairness, accountability, standards, openness, lack of gatekeeping. Decentralization is what enables us to have all of these different things. I think it might actually be possible to get these things sometimes without decentralization, at least certainly technically, but maybe not socially. So there's a lot of different types of control in these systems. There's technical control. How many nodes are running? How many validators are there? But also, we should think about things like what kinds of operating systems are they running on? How geographically distributed are they? There's legal control. How many legal jurisdictions are these nodes actually in? Can the owners of them be compelled? There's economic control. Who owns the tokens in something like a proof-of-stake system? Who has most of the user accounts? Who controls the way that these users access the application? And there's societal control, ideological mind share. Is the system really sort of focused around a few key figures who can push through changes or who can influence the direction of the system? Based on these ideas, I'm going to put up a spectrum of decentralization. So we have something like Bitcoin on the far left. There is no company behind Bitcoin. There is no foundation. There have tried to be foundations, and they have failed spectacularly. Bitcoin development right now is concentrated in 3 institutions, but actually quite widespread around that. One of them is actually my own. We employ 2 Bitcoin core developers. But Bitcoin, I think, is our standard, our flagship for decentralization. Ethereum has a foundation. The founder is still present and is involved in protocol discussions. So I'm going to put Ethereum a little bit to the right of Bitcoin. Then we have other cryptocurrencies. We have permission blockchains. Now, something that you might find interesting is I put permission blockchains as being more decentralized than these so-called ICOs we're seeing, or initial coin offerings. Because quite frankly, if you can do an initial coin offering, if you can raise money, that means that there's an organization behind what you're doing. There's someone taking the money. At least in permission blockchains, you have a lot of different companies usually working together. And then on the far right, we have your traditional type of database. Now, you might say, hey, Neha, why would you actually put Bitcoin all the way to the left? I've heard that mining in Bitcoin is actually quite centralized. Most of the miners are in China. There are a few very large miners. What you can see here is about 4 of them comprise over 50% of the hash rate. And this is where we get into the question of decentralization and what it means and what we're really trying to achieve. This seems really bad until you actually unpack the layers and take a look at how Bitcoin actually works. Because the miners don't have as much control as you might think that they do. And we've seen this play out in practice. There's groups in Bitcoin. There's the miners, of course, but the miners can't just do whatever they want with the protocol and the blockchain. The miners are running a business. They're trying to make money. And there's no way the miners want to run their mining equipment on a version of the blockchain that doesn't have economic backing. They wouldn't make any money. So the miners are dependent on the users. Which version of Bitcoin do they value more? Users are dependent on the miners and developers. They rely on the miners to actually provide the security and keep the blockchain from forking, to make it hard to double spend. They rely on the developers to push fixes to solve security bugs. Developers can't do anything unless they get the agreement of the miners. The miners are the ones who are actually running their code. So it kind of forms this tripod, this nice tripod of control. Now, one thing I do want to point out here is that this is a proof of work-based system. In a proof of stake-based system, the users or holders of the cryptocurrency and the miners are actually the same. So it's interesting to sort of think about the question, how stable is that kind of a system? And there are other actors that I think we don't talk about enough when we talk about decentralization. In particular, the influence of exchanges. Exchanges have a tremendous amount of control in cryptocurrency ecosystems. They can choose what coins to list, and in fact, a lot of exchanges charge a pretty penny in order to list a coin. Once a coin is listed, that provides liquidity. It really helps the price of the token. Exchanges can decide whether or not to even support a fork when there's a dispute with a cryptocurrency. If they choose not to support the forked token, then obviously that affects the price. And exchanges get to choose how to label things. Users go to an exchange intending to buy some cryptocurrency, and they're going to look at the cryptocurrency and look at the names and choose based on that. Exchanges get to set those names. And we saw this happening when Bitcoin forked. Both sides were kind of fighting for the Bitcoin moniker, and exchanges had to kind of make the decision ultimately of how to label things. Now, exchanges are responding to the community at large, but they do have quite a bit of control. This sort of makes it sound like I'm suggesting that we need to regulate exchanges very heavily. I want to make it clear, I think in this industry in particular, a regulatory moat too early could really stifle competition. We could end up with a few small, large exchanges which have a tremendous amount of control. So I really think it's important that this industry has a lot of competition. So that's a little bit about consensus and decentralization, but now I want to get at the remaining challenges in this space, because it's all about trade-offs. In order to get this system in which very few people actually have control, which is very spread out with all of these features, there's some things that we have to give up. One of the first trade-offs, one that I'm particularly worried about, is around security. Because you see, these systems are very hard to upgrade. You have to get the agreement of everyone to start to run the new code. And remember, developers don't really have the ability to just push out an update when they want to. What this means is that it's also hard to push bug fixes. It's a really challenging problem, figuring out how to upgrade a live cryptocurrency when there's a bug. And really, who are you even supposed to report bugs to? These things are supposed to be decentralized. No one's in control. So why should some actors be privileged about this information, that there's a vulnerability? This is a problem that my group at MIT is tackling head on. We formed something called a cryptocurrency security working group. I think this is something where the whole industry has to come together and think about things like standards and communication channels for how to deal with vulnerabilities and bugs. We hope to be a nexus for cybersecurity collaboration and set up infrastructure to help strengthen layer 1 of cryptocurrencies. Now, another important trade-off and sort of issue around cryptocurrencies is around scalability. You've probably heard this before. Bitcoin doesn't scale. It can only do 7 transactions per second. There are all these other new cryptocurrencies which can do thousands of transactions per second. I want to make it very clear, Bitcoin doing 7 transactions per second is a choice based on 2 numbers in the code. One could change these 2 numbers very easily. However, people want to balance decentralization with scalability. You see, the problem here is in cryptocurrencies and blockchains, we want everyone to be able to verify and validate what's happening. That's what makes them open. That's what makes them secure. And in order to do that, there's sort of a fundamental limit on how much performance we can get out of these things. If every computer in the entire network has to verify every step of every smart contract, it's just not going to be a very efficient system. These are not scalable systems. So there are some solutions. There's some hope. So I want to briefly touch on 3 solutions before we close. One is the idea of committees. Instead of everyone voting and participating in the protocol, we can elect a smaller committee to do so. There are a lot of systems that take this approach. There are some trade-offs here. Imagine a company that is run by a CEO versus one that's run by a set of VPs or a board. With the set of VPs or board, the more that they are, the more people checking, sort of the more sure you might be that the company is doing what they're supposed to do. If there's a small number of people in charge, it's harder to check up on them. Another technique is called sharding. This is the idea that you divide the data up and everybody takes a portion of the data to validate and secure. Imagine that you were a professor and you had to grade the final exam for a really large class, say the beginner intro computer science class at Stanford, MIT, or Harvard. They're growing like crazy. So one thing you could do is you could grade all the tests yourself, all 200 of them. It would take a really long time. Another thing you could do is hire 10 TAs or teaching assistants. You could divide the 200 final exams up between them, and they could each do a portion in parallel. This is obviously going to go a lot faster, so this is the idea behind sharding. Now, the problem here is that you have to deal with quality control between the different teaching assistants. You're probably going to have to do some coordination between them to make sure that they're doing the right thing. The professor is probably the stronger grader. The professor has seen more courses, so the professor might have to spot check the other teaching assistants. These are the challenges that arise in sharding. But I think really fundamentally, a lot of people are viewing blockchains the wrong way. They're not a system for data storage. They're not a database. They're a piece of a puzzle, an anchor of trust. And so I think the real way we should be using blockchains is we should put as little on them as possible. This is the idea behind techniques known as layer 2. The idea here is to use state channels or payment channels, and there's something called the Lightning Network, which is doing this for Bitcoin today and is deployed. Now, this is very cool, and I think it's a great idea, but there are also challenges here. It's very difficult to write applications in this paradigm. It's much easier to write an application if everything just runs on the blockchain. And there are also a large number of questions that arise around the topology of these layer 2 networks and their security. So that's all I have for you today. Thank you for listening, for being an engaged audience, and I hope that you learned something about consensus and decentralization.